Save it. Okay, good morning, students. I hope you can hear me, right? So let us start this class. I'm going to share the screen. Just give me one moment. Okay. So can you see the screen? I hope all of you can see the screen, right? Okay, good. So we were here in the last class. So we were discussing that remote sensing application, especially for disaster monitoring and mapping. So on the left hand side of the screen, there is a flood model, which is actually simulated using remote sensing data as well as ground data. And then this information is coming from the Mekong Delta. Okay, so it involves 2-3 countries. On the right hand side of the screen, it is also a very interesting application of remote sensing. Here you can see the city, or probably you haven't seen the city because it is obscured by clouds. Let me tell that this is actually the capital city of Indonesia. So this is Jakarta. Here you can see it on the screen. And then this is the city of Jakarta. And then there is a satellite image which has been captured on 19 January 2013. So on the right hand side below on the screen, there you see that there is a red and yellow and blue color overlapped on top of the Jakarta city map. So this indicates, this different colors actually indicates there is a very acute problem which is happening right now in the city of Jakarta in Indonesia. I don't know if you have heard about land subsidence. Have you heard about land subsidence? Land subsidence. Have you heard this word of land subsidence? Huh?
No, sir.
No. Okay, let me tell. So normally we know that we have the ground where we normally build our structures, and below the ground there are aquifers, or aquifers means reservoirs where the groundwater is being stored. So if you withdraw or draw too much of groundwater, the void spaces are actually filled up and by the land above, and in this process the land uh, subsides or it goes down. This is known as land subsidence. So if you're having a problem of land subsidence, probably you will see that there are some deep, how to say, patches of lands which suddenly actually goes down. So this problem is going to happen in some of the portions in Guwahati city also, because in the city of Guwahati we are withdrawing a lot of groundwater, and many of these urban developments, the water supply is 100% dependent on the groundwater. So if you draw too much of a groundwater, this problem will probably be arise. And this problem is very acute in places like Jakarta, and then in places like Bangkok City, even in many places in cities in Japan. So remote sensing is being used to map uh, how much of the land actually is subsiding in the places in the city of Jakarta. So if you see those areas in red color, particularly in these areas, these are indicative of a positive land subsidence. That means land is subsiding in those places. So you'll see there is a indication of how much of a land is being going down by the numbers given there. So minus 2.1 meter. Some places it is minus 0.5 meter, minus 0.7 meter. Okay, in the acute cases, it is going up to minus 4 meter. So minus 4 meter is a huge amount in terms of the depression or the land that is subsiding in places. So if you think that your own home, or sometimes in case my home actually goes down by 4 meter, what will happen? There will be water that will be coming from the nearby areas and trying to fill those depressions. So in this process, actually what happens, in the places you will see it in red color, these are actually filled by water coming from the sea, because Jakarta city is situated near the sea. So people actually cannot live in these areas. So right now, the government of Indonesia is actually thinking of shifting the entire city to somewhere into the south of their country. So it is a major event in terms of relocation of resources, as well as in terms of replanning of everything. Uh, just the whole city is going to be shifted, because people can no longer live in those areas where the city is falling into the zone of land subsidence. And the land subsidence is happening basically because of the withdrawing of water. At the same time, increasing of sea level. As we are discussing in the last class also, sea level is rising gradually. You see, sea level is rising and my home is going down because of land subsidence. And in this process, the water from the sea will just enter in my areas, and those places will be rendered uninhabitable. So the government has no other option but just to shift the entire city into a different uh, area inside the country. Okay, so some of the other incidences of remote sensing. Okay, so let me tell you the story. So these red and yellow and then blue areas are actually mapped from the space using a technique called interferometry. So in terms of interferometry, it uses a technique where this area is mapped by uh, two nearby sensors going together, and it is done in microwave band. So we are not going to really discuss into the technique of interferometry, but for your just information, I'm telling that this land subsidence is being able to be mapped from the space by a technique known as interferometry, which is actually which uses remote sensing or sensors which are on board those satellites. So this is a classical example of an application of remote sensing in cases of disaster mapping or monitoring. So recently, just in the last year, we were witnessing in the news that the Amazon was actually burning at an unprecedented rate. So these are actually the events which are being mapped from the space where the forest or Amazon was burning. Why is it so important? Because we know that all these greenhouse gases, most of them, which are being produced by many different countries in the world right now, it gets purified, or a part of it, or a major part of it gets purified by the tropical rainforests, because these forests, they consume the carbon dioxide and in return they give us the oxygen. So these are acting as a lung of the world. And then Amazon actually consists of a bigger chunk of these tropical rainforests. So if the Amazon was burning, that means our lungs are actually burning. So in terms of purification of the air, or in terms of degradation of the entire uh, airspace, it was a major incident. and people actually blame partly due to climate change and partly due to the policies of the Brazilian government of the incidences that happened in the last year. So those red areas there on the screen on the right hand side, you see those are known as the hotspots. Hotspots means those are the areas where fire was occurring at a particular day or a particular time. And this was actually mapped by uh, VIIRS and MODIS satellite data, and this was captured on the on an event August 13, 2019. So almost exactly 1 years ago. uh, 1 year ago. And you can see almost all the places, these are the red dots, and then these are representing the forest fire that were occurring. So it involves parts of Brazil, Bolivia, Paraguay, and then on top, Venezuela, those countries. Okay, and then on the left hand side, you see the same incidents, but this was mapped with a high resolution satellite image. So on a high resolution satellite image, you can actually see the forests that are being burned at a particular area. So what is the difference between a high resolution satellite image and a low resolution image or a medium resolution image? Eventually, when we will be entering the class, we will discuss those things. But for the time being, just you see that these are the images which are capturing the individual burning events, and then on the right hand side, you can see it on a regional scale. And those red dots are the fire hotspots that happened in the Brazilian forests. Okay, so another example is this one. This is actually from our own South Indian state of Chennai. So Chennai is a typical example of a crisis that is actually waiting to happen, uh, probably in many other cities. So it did happen in 2019, just last year in June 15. Let me tell you the background of this incident, because the entire Chennai city is dependent on a lake, okay, for its domestic water consumption. So the whole city of millions of people are dependent on this particular lake, which is actually in the middle of the city, for the water to be consumed for the daily uses. And if you just imagine individual spending almost 20 to 25 liters of water every day for its individual consumption, and multiply those numbers with the total number of population in the city, you will get an idea how much of water actually is in demand for the city almost every day. Uh, this left hand side of the screen, here you see the lake in the full capacity. It was in the year before 2019 and 2018. This is also the same satellite image. On the right hand side, it was captured in June 15 in 2019, and you can see the problem. The reservoir or the lake is getting drier and drier, and then there is no water there. So the entire city has to actually, it came into a halt, and then government issued statutory warnings, issuing strict consumption and rationing of water during that period of time. And then from the captured image here, you actually can calculate the volume of water on the lake, or an approximate volume of water on the lake. And through this, you can make some planning movements, how much of the water that has to be rationed until we get further rainfall, and then the reservoir is actually filled up with water back to its full capacity. So these are some of the examples where remote sensing technology can be or has been in use, particularly for uh, disaster uh, monitoring and then planning. So this is also a kind of disaster. You can, in terms of disaster, it will come into the category of drought. Okay, here you see a photograph of what happens during this time. Okay, so there are few application areas in civil engineering. I will not go too much into the detail, but at least you should be knowing these things When you come to water resource engineering, that means how much of a water is there as a resource which can be used. So normally we often hear that we are having the big river of Brahmaputra, but at the same time, our government, both the state and the central government, actually are failing in terms of using the water, which is actually a resource, to its full capacity. But forget about the full capacity, even maybe not to its 20% of the capacity. So a major challenge in terms of engineers or in terms of planners, it depends how somebody can make use of this resource and then uh, uplift the quality of life. So here on the red area bounded that you can see, this is known as the basin. So do you have any idea about the basin? BASIN, basin? Basin. BASIN. Here I write down on the screen. Do you know what is a basin? Yes or no? Hmm? What is a basin? Can you hear me?
Basin is a class of land drained by a river and its tributaries.
Okay, so yeah, that's to some extent this is true. Who is saying this? I cannot really. I couldn't see. Who is this? Is it Takar? What's your name?
It's Yodame.
Huh? Can you write your name here
Yodame.
in the chat box?
Okay.
Yeah, this I need to see. Who is this? Hmm. Okay, good. So you were from which faculty? From basic science?
Yeah, from science faculty.
Okay. So I was expecting the similar answer. Probably those students which are not from the science background. Let me explain that. Basin is very important in, or the word basin is very important in terms of water resource management or in some engineering applications because uh, it tells about the boundary where if a particular rain is falling or a particular drop of rain is falling, where a part of this rain will go. So this will be governed by if it is falling on a particular basin or if it is falling on another basin. Just an analogous example, maybe we have a basin, right, where we wash our hands sometimes, or nowadays we wash our hands many times. So when you open the faucet and then you wash your hand, all the water that actually gets accumulated in the basin, it has a common element that all the water that is accumulated within the periphery of the basin, it goes out through a common outlet. So if somehow if you spill water outside the area of the basin, that water will not be going out through the particular outlet. So in natural world also, uh, if there is a rainfall that happens somehow outside this red boundary, that part of the rainfall will be going to a different river other than these rivers. Okay, these are the black lines are the rivers. So ultimately, a rain falling somewhere here, a part of it may go to this tributary, and then eventually this will be going into this tributary, and ultimately it will be joining the major river here, and then it will go again to form another big river, and then ultimately the water that was falling here will eventually go out through this particular outlet. Can you see it on the screen, the cursor? So this is the concept of the basin. Because if you want to plan any water resource, or if you want to really manage your waters, you cannot really go by the political boundary. So what I understand by the political boundary is that, or the administrative boundary, uh, in Assam there are different districts, or in India we have different states. But if you really want to manage the waters of a particular river or a particular tributary, you cannot be guided by the political demarcations or the administrative boundaries. That is why we have to rely on a different map, which is known as the basin map. So this basin map, which is actually the outlined red map, may fall into different districts, or it may even cross the boundaries of certain states, or even it may be some trans country rivers. Some of the big rivers like Brahmaputra, or some of the big rivers like Ganga or Mekong. So as I said, Mekong River, the basin boundary actually falls within 5 countries. Similarly, in Brahmaputra, it falls. The upper part of the river is going into Tibet, now in China. Then partly it is in India, and then Bangladesh, and also a small part in Nepal. So you see there are like 4 countries where the basin actually falls. So in order to manage the resources of the water that is a part of that basin, all these countries or all these districts or states have to have a mechanism that information flow happens the way it should between these states or between inter districts. So if sometimes there is a rainfall that is happening on the upstream of this basin, and this is actually falling into a different state, this information, if it is not shared adequately with the states which are at the middle part or at the downstream of the basin, the people who are falling into these areas, particularly in the downside of the basin or the middle part of the basin, for them it would be difficult to manage these waters, because you have to issue a warning, and then the warning will be issued only when you monitor how much of a rain is happening on the upstream of the basin, and this information has to be shared by the state or by the district which is actually falling in the upper part of the basin with the middle part or the lower part of the basin. It may so happen that this part may fall in a different country, the middle part may fall in a different country, but if this upper country doesn't share this information with the other parts, the people or the governments which are actually part of this basin will have real difficulty in understanding uh, the flood in the river, and at the same time when the water will go down. So in terms of resource allocation or resource planning, they will face a lot of problems. So there must be some adequate information sharing that has to happen between these states or in between these districts. Okay, and for that many government departments have to come together. So when talking about remote sensing application for this particular purpose, um, how do you think that the red boundary is being demarcated or is mapped? So nowadays we have satellites which capture the undulations of this art, and actually this undulation is shown in this this image down below. So undulations means in your area, what is the height that you are standing from someone's from a neighboring area. So there may be ups and downs, right? If you go to our university also, there are places where you have higher elevations, and there are places where you have lower elevations. So sometimes you will have to walk up, you will have to go down. So these are known as the undulations. So these undulations can be captured by the satellites, which are flown or flying above, and ultimately these undulations will help you to delineate this basin boundary. Okay, so these kind of a map are known as digital elevation models. So it is also known as DEM. I'm writing it there. Okay, digital elevation models. So different satellites are there in order to capture this information, uh, mm, which are very important in terms of water resource engineering or water resource management. And then it also is nowadays used for planning purpose. Okay, let me see what is it written here. Watershed analysis. Okay, so these are the same thing that I just explained. So the remote sensing images are also used for water resource management, which is a part of civil engineering. So if you talk about particularly its application areas in disaster mapping or monitoring, earthquake is a major disaster or natural disaster, which is very difficult to predict. So this is one of the areas where still now people are scratching their heads how somebody or how a country or a nation can or a department can predict an earthquake before it really happens. So this geological phenomenon is different from other natural disasters in the sense that it happens abruptly, and even if we try with our latest technologies, we fail to really make its accurate prediction. Uh, but what we can do when the earthquake happens or the moment it strikes, with nowadays with advanced technology, we try to minimize the damages that it can cause. So one of the secondary damage of an earthquake is there are many other damages of earthquakes, but uh, secondary damage means the damage that is triggered by the primary damage or primary incident. So the primary disaster in this case, if it is earthquake, there may be secondary disasters which may be fire. So if you are in an environment where there are urban structures everywhere, so if there is an earthquake and then somehow the structures they collapse, and then you have a constant supply of electricity, there will be definitely these type of secondary disasters. So for example, this may be fire. So a classical example of a fire after an earthquake is the Kobe earthquake scenario in Japan. Uh, so during that period of time, the number of people which were killed by the fires were actually much larger than the number of people who were killed or who actually vanished because of the primary earthquake itself. So sometimes these secondary disasters are uh, more catastrophic in nature, or it causes more damage than the primary disaster. So in this case, this is a satellite image, and this is a satellite image captured by a Chinese satellite, which is known as ZF2. And this is actually coming from, this is not from China, okay? This is coming from a dam in Iraq. Okay, so in this, here you can see the lake where the dam is supposed to be constructed. These two red areas. And then there is a road that is leading to this dam. And after the earthquake, a part of the road is being collapsed. So this linear structure is a road, or it may so happen that this is a river that is feeding this lake. So if there is a landslide that obstructs the flow of water into the reservoirs, what may happen? Hmm? For the time being, just you see that these are the images of a pre-disaster scenario and then a post-disaster scenario. So the pre-disaster scenario, there you can clearly see the road which is not obstructed. So here on the right side of the screen, you see this linear feature or linear structure is the road. And then after the earthquake, here you see that landslide actually happened because the earth's movement or the earth shook. And then there are debris or the volume of uh, soils which came down, and then this actually obstructed the road here. So as a person who is engaged in disaster mapping or monitoring, he has to plan how much of a land has to be cut in order to reconstruct this road. How much means in terms of volume of soil that has to be excavated. So you have to allocate how many excavators need to be there for a particular point of time. If it is a very emergent situation, then probably you will have to send the maximum capacity of excavators, or you can specify the size of the excavators, how much, or you can really plan how you are going to excavate this land. So the similar situation just happened a few days ago on the way to our university also. So the approach road was obstructed by a landslide. So this was not an earthquake induced landslide, but this was a rain induced landslide, the one that happened recently to our university. So in that case, there was only one excavator which was used to clear those debris, and then finally it took almost 1 day. So in this case, probably you'll have to plan accordingly, and then if you have a remote sensing image, you can do this planning pretty well. Okay. So in a similar situation, if you have a high resolution satellite image, you can actually see the total number of buildings which are actually collapsed after an earthquake. So this is actually the same kind of a situation. So here you see you have a high resolution satellite image. That means you can see the buildings or individual buildings quite clearly in those images. And then this is a pre-earthquake scenario somewhere in 2017. I also cannot read these characters. So just by the year, you can imagine this is somehow in 2017, and then this was the image. This is an image which is after that particular date or particular year. So somehow in between, we have an earthquake incident, and then this caused many of these buildings to be damaged. So in this case, damages are of various kinds. Sometimes what happens, a building, if it is erected like this, because of the movement, it may just give away like this. Sometimes if the building is sitting like this, it may just collapse like this. This is known as the pancake collapse. So if from a satellite image, you can really see the total number of buildings which are actually witnessing these damages, and also you can categorize what kind of a damage actually has happened in those buildings. So if it is a building that is damaged because of liquefaction of the land, liquefaction of the soil, where the soil behaves as water during the movement of the earth, in that case the building will just give away or collapse like this in the lateral direction. Or if the building has really structurally collapsed, and then it is a pancake kind of a collapse, where this classical example may be the 9/11 terrorist attack, when the building actually gave away and all the floors actually collapsed like this. So this is a classical example of a pancake collapse. So all this kind of categorization can be done with these high resolution satellite images. Okay. Okay. So these are actually the situations where you have a disaster and then you are trying to map or monitor the damage. Okay, but if it is not a disaster, also during that time, also remote sensing has a lot of applications. This is particularly an area where we see application of remote sensing, uh, particularly in crop monitoring and growth forecasting. So here we have a remote sensing image of different months, which is monitoring the growth of the crop. Okay, this is an Indian remote sensing image, and these red areas are actually, you will later on know that these are captured images in the infrared region. So when trees grow, right? So it is actually monitoring the how good is their growth over different months. So it is starting from mid-November, then early December, early January, then mid-February and mid-March. So these red areas or red or the intensity of the redness of these pixels in the image, they represent the vegetation vigor or the strength of the vegetation. So we can really monitor how much is the growth or how good is the growth. So if there is some slump in the growth, you can take some intervention measures, especially if we notice that there is not a growth which is expected on a particular cropland. So we can really analyze, and the scientists are there, which who will just tell what needs to be taken in order to maintain the growth of these crops or any kind of vegetations. So just for the timing, remember that the redness of these pixels indicate the vegetation vigor or the growth which is expected. So if it is a small patch of land, sometimes we have our own land where we cultivate. Assam also, not only Assam but as a whole, all over India, we are people who are majority of the people are agriculturists, and then we see this thing happening. Sometimes we notice that if there is a rainfall which is not happening in due time, it may affect the growth of the crops. But if you have to monitor this thing in a larger scale, in terms of the whole district or in terms of the whole state, it will be difficult unless or until we monitor this thing from the sky. And then how do we monitor this thing? We monitor it with the help of remote sensing satellite images. Okay. So later on also we will get a chance to calculate this vegetation vigor when we will be able to download certain images, and then I will give you how to calculate a particular index which is known as NDVI or normalized vegetation index, normalized difference vegetation index, which is indicative of the growth of vegetation. So starting from November up till March, or even every day, you can monitor the growth of a particular crop. Okay, so you can forecast how much of a yield is expected at the end of the crop season. Okay, so let me conclude with these things for the time being. That with the launch of Sputnik 1 by USSR back in 1957, so we have entered a new era of Earth observation. So why I call it a new era? Because remote sensing technology or space-based monitoring technology was uh, there even before, but that was at its very formidable period. And this science took acceleration. This science actually advanced because of the Cold Era competition. So there were two countries, mostly the USSR and USA, which were driven by this competitive nature. And then mostly this technology was confined within the military people for their own application areas. So it was not open for public until 1972. So since 1957 to 1972. So the second conclusion is that since the launching of the Landsat series of satellites in 1972, so as a technology or as a device for monitoring, this is quite a new subject. That's what I want to emphasize. Because only after 1972, this remote sensing has crossed the boundary of its application, which was only in military use before, and then now it has given its way for the civilian domain. So we are being able to see or make use of this technology with the launch of Landsat series of satellites in 1972. Then the third one is that use of remote sensing data has boosted the use of gridded information and then their analysis. So what is a gridded information? So if you have looked into a chess board, right? Sometimes you may have played chess. So these square boxes are known as grids. These are not really grids, but the boundaries of these boxes, which make them the boxes, are known as the grids. So gridded information is that when you capture an image, this information is stored in individual squares or pixels. These are known as pixels, Pixels, which is also a short form of uh, picture information. Okay, so this gridded information and their analysis actually helped or has helped with the advancements of remote sensing technology. So if you have a gridded information, you can do this gridded analysis. So in a particular area, what will happen in your land? What will happen to the neighboring land? What will happen to the neighboring land on the north? So this kind of information is now helping the gridded analysis. Before we didn't have a gridded analysis. We have a information a lump sum analysis, or we call it a lump sum model. Okay, gridded modeling or gridded information analysis was possible or has advanced with the help of remote sensing images. So the next one is that it is found as application areas in climate change monitoring. So these areas we have shown with examples before. Water quality monitoring. So water quality also you can monitor. The quality of water means how good the water is for domestic consumption or for industrial use. Just you don't have to go too far. So if you just want to analyze the water quality of the Brahmaputra river within the Kamrup metro area also, you will see that the water quality probably is worst where the Borolu river is meeting the Brahmaputra near the Fancy Bazaar area. Okay, why? Because all the industrial wastes are being dumped into the Borolu river, and then the Borolu river is meeting the Brahmaputra river at that particular junction. So if you just collect water from that junction and you test it in the laboratory for the standard water quality indexes, you will see that these are falling way below the normal range where the water quality should remain for any application. The same thing can be monitored from space. So that is what I want to say. So if just in the particular stretch of water in the Brahmaputra river, we want to monitor it, supposed from upstream and then in the middle and then in the down, you can get an indication. Just a moment, just take me, let me take the phone. Oh, Manos, boy, class up. Oh, Korea, okay. Then crop growth forecast. So as I just showed you, then disaster management. So disaster management, we have seen quite an example of disaster management is starting from floods, then glacier lake outburst, and then monitoring of the glaciers itself, or the land subsidence, or the forest fire, or what else? Uh, Earthquake, building damage assessment, those kind of things. Then water stress evaluation. Water stress evaluation means how much of a water actually is needed by a particular crop or growth for a particular growth in a certain point of time. Okay, so that will be monitored or that can be monitored. Land subsidence and a lot of other fields. So the more you enter into the subject, you will see other application areas, uh, including many of the application areas which are actually combined together with other fields of research. So it is not only, though it is the heart of it is actually based in pure science and engineering and electronics, but its application areas has found its domain crossing many other disciplines. So you will see a lot of application areas in social science. Even if you will see that you have the application areas nowadays uh, in that will depend the outcome of an election. So many other application areas. So we have seen increasing use of satellite-based technology in civil engineering. So particularly in civil engineering, maybe hydrology, surveying, or building site investigations. So these are just a few application areas. In particular, in case of Assam, a lot of application possibilities are there, but it has not really been utilized to its greater potential. So that is where we need a lot of people who are really willing to come forward and bridge this gap between the science and the end beneficiaries. Okay, so I hope possibly if you learn this subject, you can fill up this gap. So as I said that how we have to generate the awareness. So the greatest threat of the civilization is climate change. So if you just happen to be some of the ambassadors or some of the people who are willing to work in order to bridge this gap between the science, because science is already there, scientists are predicting many things, but the people or the end beneficiaries, they are unaware, they are not actually working in the direction, especially in the country like ours where we have a lot of gap in terms of poverty. So it is really difficult to bring everybody into a common board and agreement. For that, we need a really dedicated amount of people who is willing to work in this field. So hopefully, uh, some of you probably will be willing to work in this direction later on in life. Uh, for that, we need an environment of awareness and knowledge transfer, which is very much needed. Okay, so eventually we are actually coming to the end of this presentation. From the next class, I will go straight into the syllabus, and then I hope everybody has a copy of the syllabus. So the syllabus, as you can see on the screen, it starts with the first module, which is about hazard, risk, and vulnerability in disaster. So in this case, my strategy will be that I am not going, sometimes I will emphasize, or sometimes I may spend 2, 3 classes on a particular topic, which I feel is really important to describe. And then I will just not equally spend all the time on all the topics because that possibly will not be able to happen. So the areas which I feel needs to be emphasized, I will give more emphasis. Okay. Oh, just a moment. I just like to share the link where you need to fill up your attendances. Okay, it is given there. So you just fill up the form and then quickly give your attendances. It will remain open for 15 minutes after the class is over. Uh, and then we will start with our hazard, which is a hazard, risk, vulnerability, because these names you will often hear in the conversation or in day-to-day